Hello everyone. In the previous lecture, we have seen about the discrete probability spaces, and we have refreshed our knowledge on the discrete probability spaces. In this lecture, we will move on to the next concept, which is related to the sigma field first, and then we move to conditional expectation in the later part. But before we go into the filtration idea, so let us review our again one more review about our what we know about the binomial model that we are going to stick to from now onwards when we deal with the discrete time models. In this simple binomial model, what we are assuming is that the stock prices are going to follow the simple binomial model that we are going to describe. What we are assuming is that at each time step, the stock prices is going to go up by a factor u, or it is going to go down by a factor d. Now, as you see, since this is the outcome is binary, we can associate with this a simple experiment as if there is a coin toss takes place and results in head, then the stock price is going to go up, and if the coin toss results in tail, the stock price is going to go down. Right? This is a simpler model. You can associate, since this outcome is binary outcome, you can associate a coin toss to each of these movements. At each step, we will associate a coin toss. So, the whole movements over different time periods can now be associated with more and more number of coin tosses and the resulting outcomes. That is the model that we have in mind, which we have seen earlier in the lectures, the binomial model for asset pricing. Okay. So, what we have is the binomial model for stock prices, where we say that the price moves up by a factor u if the coin toss results in head, or the price moves down by d if the coin toss results in tail, which we denote by h and tail. Note that we are not specifying the probability of up or down movements, we are just looking at the values of the stock prices, which is what you have it here. Now, consider for our simplistic setting, for simple example, you assume that there is a sequence of 3 coin tosses, then the collection of all possible outcomes of these 3 coin tosses can be enumerated by So, this sequence of 3 coin tosses will result in any one of these 8 possible outcomes. So, this is our sample space for this experiment, and these are the 8 possible outcomes that you have for this. So, a typical sequence of this would be denoted by a small omega which will belonging to omega, where this omega can further be written as omega 1, omega 2, omega 3, where each of these omega i's would be either head or tail. Right. Now, whenever we require, we could use the full omega, or sometimes if a part of it would also be used when we are considering certain random variables. Say for example, if you denote S k at omega as the stock price at time k for the sequence omega, right. So, this omega typically depends on all 3 in this particular 3 coin toss, otherwise if you go for it you will have more. So, you could see that we could write in variably like S1 of W, which is be the same as S1 of omega 1 omega 2 omega 3, which we could also write it as S1 of omega 1, because the stock price at time 1 is really going to depend only on the first toss, second and third toss will not make an impact. So, in such a situation we might also write this, whether we write S1 of omega or S1 of omega 1, omega 2, omega 3, or S1 of omega 1 for a particular omega would be clear from the context, and all 3 will be used interchangeably. Similarly, your S2 of omega could also be written as S2 of omega 1, omega 2, because to determine stock price at time 2, at least 2 outcomes are needed, third outcomes is irrelevant, because for any of those W3 this is going to result in the same value. In that context we will use this notation. Now, you can see that if I take this omega and my f to be the power set over omega, right, I could see this Sk, which is the stock price at time k, as a random variable. If I define, then all these random variables Sk, they are all random variables are defined on this along with whatever the probability measure that you define, right. They are all this f measurable. Later you might see, you will see that these are in fact measurable with respect to a smaller sigma field. Now, if I look at this particular example of 3 coin tosses, then my f is power set of omega, which is going to have 2 to the power 8 element, which is 256 elements. So, this is with respect to that sigma field that you can see that this is measurable. Right. Once you have this example in mind, okay, if you are so comfortable, you can even draw out a picture starting from some initial time period, which starts with a value of S naught, and at time 1 this can become either S1 H, which is going to be U times S naught, or S1 tail, which is going to be D times S naught. So, this could be any one of these 2 values, and in this is at time 1, and at time 2 I would have S2 of HH, which is value is going to be U squared S naught, or this can become my S2 of HT, which incidentally if I draw out, this will also be of S2 of TH, this will be U D S naught, and this one, this node would be S2 of Tt, which is value is going to be d squared S naught. So, this is at time 2. So, the stock prices, if I denote, so then this would further become first S at 3 would be U cube S naught, S at 3 of this, which is equal to S at 3 of, which is equal to S at 3 of so, this will be the evolution of the stock prices for the 3 time periods. It may start from S naught, it may go up by a factor u, which becomes, it may become U S naught, or it may be down by a factor d, which means it would become d S naught, which we would say that it is S1 with head. Okay. As we denoted, you can say S1 head 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 is the same as S1 head head tail, right. Like that, if you can enumerate all 8 possibilities, all of them would result in the same value of U S naught. So, we simply denote it by S1 of H. Similarly, for S1t and S2 of head would be this value, and S2 of HTTH will be equal to UD S naught, and S2 of TT will be d squared S naught, and so on for the 3rd time period, where you would see that there are essentially 4 possible values that we have. So, what we are essentially saying is stock price in 4 time periods become one value, becomes one of these 4 values. So, that is what this binomial model basically describes, how the stock prices evolve. Okay. So, let us please keep this figure in mind, because for at least another 3 or 4 lectures. So, when we keep referring to the binomial model, we mean this setup, and every time instead of maybe we writing this, we may just draw out this picture, then it is to be clear that what we need at each node, or what we meant by the values of the stock price at each node would be clear from this particular figure. Okay. So, this you can remember this figure in mind, so that it is easy to understand what is happening and what we are trying to do with respect to this, or in this binomial model, when we are trying to do at least in the complete discrete time asset pricing models. Till the time we are going to, and this can be extended to any number of time periods. Only thing is, this binomial tree, this is called as recombining binomial tree. So, this binomial tree will keep expanding in each, and if you have n periods, then it is going to have n plus 1 values at the fag end. That is the idea that you will have, and the number of possibilities coin toss if you have to assess, then if you have n time periods, then you are going to have 2 to the power n values, or 2 to the power n possibilities. Some of them will result in the same stock prices as happens here. Now, with this binomial model in background, we keep referring to this, we will come back to this for each example. We will now next look at the idea of, in this binomial model setup, sets determined by the first k tosses. So, this is the idea that we look at now, that the sets determined by the first k tosses. Now, what we mean when we say that a set A, which is a subset of omega, is, we say that this is determined by the So, we see that if a subset of omega, if we call it A, we say that this is determined by the first k tosses. If knowing only the outcome of the first k tosses, we can decide whether the outcome of all tosses is in A or not. So, given an omega, which is an outcome of all tosses, now if this set is given and if we can say for sure that whether that omega will belong to this A or not, if we can say that, then that set is determined by the first k tosses. So, this is the first k tosses idea that you have it here. Now, if we collect all those sets that are determined by the first k tosses, okay, and we call that collection as Fk, then it is easy to check that this collection is a sigma field, which means that it is having the property of the sigma field that this is a non-empty collection which is closed under complementation and countable union. So, in this case there will be finite, so of course it will be finite union will do. So, if you collect all the sets that are determined by the first k tosses and that collection if we call that as Fk, then this script Fk would be a sigma field, and you would also observe that the Sk that we talked about, the stock price at time k, is also Fk measurable. Now, it will be clear once we write down some of these f's that we think that how this is actually follows here. Okay. Now, let us start this. Okay. Now, when as I said f naught in the earlier lecture, that this is the trivial sigma field which we denote by f0 when that kind tosses has not started. So, this is what it is. Now, given any omega, we can say whether this belongs to each of these sets. So, these are the sets determined by no information. This is no information. Now, we are coming back to the idea of sigma fields viewed as information content. That is what we are aiming to go. So, in the case of the 3 coin toss example that we have set, or a 3 period binomial model, whichever way equivalently you think about it. Okay. Let us look at what is F1 consists of. Okay. So, what is F1? So, F1, it is the set of the sets determined by the first one toss. Okay. So, this consists of the following 4 sets, phi, omega, and we call it 2 sets AH and AT, where my AH would be all those omegas of which is there in the sample space, and that starts with the first coin toss as head, which essentially mean in the 3 coin toss experiment this, and AT would be so, these are the 4 sets that are determined by the first one toss. Now, if I pick any omega in the sample space, I could say for sure with respect to each one of these 4 sets whether that particular omega will be in or out. Okay. And hence, these 4 are the sets determined by the first one toss. Okay. And if you notice in this particular case, these are the 2 atoms for this particular sigma field. Okay. If we recall the notion of this, because these are disjoint and their union is omega, and this generates this sigma field F1. So, this is F1, and similarly if I have to look for F2, which is the sigma field generated by the first 2 tosses, we will extend this notation of AH and AT and in a similar way. So, that will be phi omega A hat hat A H T A T H A T T. So, as you would see, these 4 sets forms the atoms for this particular sigma field F2, but then this is itself is not F2 because this is not a sigma field. So, what you have to do? You have to add all the sets that are required to make this as a sigma field, and all those sets would be forming part of this F2. So, instead of enumerating all these, so I would simply write that as unions and complements of these sets. Okay, if we take, then this would form a sigma field, and you can observe that this 4, there are 4 atoms or the 4 sets which partition this omega. This sigma field then is going to have 2 to the power 4, which is 16 elements, right. Similarly, if I write the full, as far as the 3 coin toss experiment is concerned, the sigma field generated by or the if I collect all the sets that are determined by the first 3 coin tosses, which is essentially the all 3 coin tosses, then I will have phi omega A H H H A H H T and so on. So, which essentially AHH in this particular case would mean that it is just that HHH alone. So, since we are following notation from AHH means anything of this type, similarly AHH means essentially HHH and HHT is forming this AHH, and so on for AHT, ATH and ATT, and similar way if you can expand. So, this will be this 8 basic sets and unions and complements of these sets, and as you see, so there are 8 sets of this. There are 8 atoms that you have here, and you would see that this is nothing but the power set of omega, if our omega is the 3 coin toss experiment, right, and this is going to have 2 to the power 8 element, which is 256 elements, and this is what this set determined by the first 3 tosses. Suppose if you have more number of periods in the binomial model, then this would still remain as sets determined by the first 3 tosses, and in that case our AHH would be expand to include more number of elements possibly. Okay. Now, this sets determined by this. Now, if you observe this 4 sigma fields, okay, this is F naught, which is we associate with no information case, F1, which is after knowing the first toss what is going to be the outcome, or the events or sets determined by the first toss, which forms F1, which is sigma field F1, and F2 are collection of sets determined by the first 2 tosses. F3 is the collection of sets determined by the first 3 tosses, and so on if you have more number of time periods. And this essentially, if you look at these 4 sigma fields, at least you can easily recognize the following, that F naught is contained in F1, F1 contained in F2, and F2 is contained in F3, right, and these are, right, which essentially means that you have not lost any. If I go back to the information interpretation of the sigma fields, I have not lost any information, I have only added the information. To F naught, I have added the information about the first task. To F1, I have also added the information about the second task, and to F2, I have added the information about the third task, and so on. So, I have only added the information about the further tasks, or if I have to talk in terms of the stock price movements, up movement or down movement, what has happened for that particular time point, I have added that information and I formed this sigma fields. So, this sigma fields, if you observe that the previous one is contained in the next one, and this behavior is continued in this manner, right. So, we have a scenario where this is in this particular case in a 3 period model. So, this is we are saying in a 3 coin toss situation, you are observing this, right. Now, in general, so this is what you are observing. In general, you could have a collection of 0 to say some either finite number or a collection which goes on, right. This is with, so which means that now a sequence of sigma fields sigma Fn with the property is called a filtration. Okay. So, in mathematical finance, this filtration plays a important role because this is the modeling element for the information content that you have, and everything you would determine based on the information available, and the information available would be given in terms of this filtration, where as the time accumulates, as the time progress, the information accumulates and no information is lost is a scenario that we are having. So, this is what we call a filtration. This is what in this simple setup you have easily observed that F naught contained in F1, contained in F2 and contained in F3 and so on. So, in general such a sequence of sigma fields is what you call a filtration, and when we talk about this binomial model, we will say the filtration, the full complete filtration, we mean that this F2, F3 as we have defined here are in a similar manner if you are extending this to further time points. Okay. Now, so this is this the only filtration with respect to the binomial model that we may consider? Not necessary. So, we could also consider filtration could be in a different way, right. So, one other way in which we will encounter filtration is in terms of the information carried by the random variables. Okay. So, this is about the complete coin tossing. Now, we could also see in the context of this binomial model that the random variables S k's denote the stock price at time k. They also carry some information. Now, how do we construct a filtration in those informations that if I like. Now, for which if I go back to the previous lecture's idea about the sigma field generated by a random variable x, which is sigma of x, or the smallest sigma field with respect to which x is measurable, right. So, if I go back to that idea, if I use that idea, right. Now, you would see here with respect to the F naught that I have already used it, right. So, S naught, S1 would not make much difference, but let me take directly the S2 and look at the sets determined by the random variable S2, right. The reason is, if I go back and look at this binomial model, you would see that S naught is single value, S1H and S1T 2 values, whereas when it comes to time 2, your HT and TH collapses to form one single node, which is UD S naught. So, that will really help us to understand better what is this point here. So, let us look at sets determined by S2 in a similar fashion as the sets determined by the first two tosses. So, this is basically the sigma algebra generated by S2, right. So, which essentially means that if you know only the value, what are the sets determined by S2, if I extend the same idea, if you know only the value of S2, then we can determine whether a particular outcome is inside that set or outside of that, for sure. Okay. So, if I look at this sigma of S2 in this particular case, so you would see that this will consist of these two obviously, then AHH obviously, then the next element is what is the difference ATT, and so you say complement unions and complements we write, but generally if you take all possible unions of these atoms, automatically this thing will be a sigma field. Okay. Now look at here what we have underlined. So, this is the sigma field generated by the random variable S2 or the sets determined by S2, because in the node HT or TH, the stock price is simply UD S naught, and in AHH it is U squared S naught, and ATT node, TT node it is D squared S naught. So, this knowing the value of this random variable can know only then this part, which is essentially what is condensed is that there is one head and there is one tail. Which one occurred first is immaterial as far as that particular node is concerned, right. So, this collapses into a single. So, if I compare this with F2, F2 have 4 atoms AHH, AHT, ATH and ATT, but here this sigma of S2 has this 3 atoms, AHH is one element, ATT is another element, whereas this union of these two elements would form another atom, and this is what the sigma is generated by sigma of S2. But now, if I look at the same thing sigma of S naught, which is the trivial sigma field, which will be the same as F naught, which is basically phi and omega, and my sigma of S1 would be same as F1, and this will be phi omega AH AT, because by knowing the value of S1 is equal to knowing the outcome of the first task, whereas the knowing value of S2 is not exactly equivalent to knowing the value of two coin tosses, first two coin tosses, right, because here we just collapse the information into single. But sigma S2, if I look at it, this is not equal to F2, okay, but whereas F naught and F1 are exactly same as sigma of S naught and sigma of S2, and similarly if you go beyond the sigma of S3 is also not going to be equal to F3, and that is not all. So, this is the sigma phi generated by this, but here you see that sigma of S naught by virtue of that being equal to F naught and sigma of S1 is equal to F1. So, this is F naught is contained in F1, but if I look at F1 and sigma of S2, which is sigma F1 is not contained in sigma of S2, right. So, this will not form sigma of S naught, sigma of S1 and so on will not form a filtration. So, now to get a filtration, what we do is we slightly extend this concept, right, of sigma of is generated by rather than a single random variable, it can be extended to multiple random variables 2, 3 and so on, right. So, now, but easily you can see that in this particular case, this is also, we also can write this S naught S1, and what is the meaning of this sigma of x y is the smallest sigma field with respect to which both x and y are measurable. Just extend the idea, sigma of x is the smallest sigma field with respect to which x is measurable. Sigma of y, so sigma of x y is essentially what we are saying is, take the union, and that union of two sigma fields is not necessarily a sigma field. So, add whatever sets that are required to make it a sigma field and get that sigma field, and that is what is exactly equal to sigma of x y. So, this is the smallest sigma field with respect to which both sigma x and sigma y are measurable, means this sigma x y contains sigma x as well as sigma y, and it is the smallest to contain these two. So, that is what it means. Okay. So, now this sigma of S naught S1 would be this, and along similar line, if I take my sigma of S naught S1 S2 is the smallest sigma field with respect to which S naught S1 S3 all three are measurable, and which obviously will contain sigma of S naught, sigma of S1 and sigma of S2 and some more sets to make this as a sigma field. So, this is the smallest one. So, but if I take this, since this would already contain sigma of S naught, sigma of S1 and hence sigma of S naught comma S1. So, this would contain my sigma of S naught S1 and this would contain sigma of S naught, and this would further expanded by including S3, right. So, which I will write it in this position. So, this is essentially sigma of S naught S1 S2 S3 and so on. So, if I look at now this sigma of S naught, sigma of S naught S1, sigma of S naught S1 S2 and sigma of S naught S1 S2 S3, these form a filtration. So, when we say this sets determined by these stock prices, so this is another way in which you could get a filtration in this model. Either you could take the complete information case, right, which will form a filtration completely, or a filtration generated by the stock prices. That is what we will say, generated by the stock prices, or the information content is exactly same as what you would get by observing the stock prices. Remember, if I say the sigma of S2 and F2, if I compare this sigma of S2 and my F2 here, which is these two are not equal, I said the information content in F2 is more, because there you have the information about whether the first task is ahead or the second task is ahead. Whereas, when you come to sigma of S2, you see that there is you have only one information, which is that one task is ahead, one task is a tail. You do not know which one is the right. So, that is where you lose some information and then you get something smaller. So, as you expand, generally you will have more information, that is what is generally happen. So, this filtration is basically then the information accumulation. The information accumulation is what we are modeling through a filtration. So, the filtration could be a complete filtration as we saw in the previous F0, F1, F2, F3 case, or a filtration could be determined by this sequence of random variables S0, or in this particular binomial asset pricing model case, it is basically the stock prices of various time points and the filtration generated by them is in this way. So, this is another filtration that you could have. Now, we might work with either of these two filtrations as we go along both in discrete as well as in continuous time model. So, but the basic understanding of filtration is this that we have here. Okay. So, with this we will come to this filtration idea, we will close. Right. Now, once we have the discrete probability spaces and the filtration idea, the next thing that we will do is basically the idea of conditional expectations is what then the idea that we are going to explore. And as far as mathematical finance is concerned, this is one crucial topic which you need to master. It may be a little tough, and but once you understand the basic ideas with a little bit of effort, it is going to be easy for you to follow the remaining parts. So, I would suggest that you spend some time on this conditional expectation idea, explore a bit. In the discrete time it is very easy to follow, but in the continuous time when we reach, we may not be able to see what is happening, but we will follow whatever happened in discrete time, expect to follow in continuous time, and we will go ahead. So, there we will quickly move through, but in discrete time please spend some time to understand the notion of these conditional expectations. To start the notion of these conditional expectations, let us take the ideas from the conditional probabilities and try to take it forward to reach to the conditional expectation. Recall in the previous lecture we defined at the end, towards the end, the conditional probability and the conditional expectation of x, a random variable x given a set A. Okay. Same idea that we are going to follow here always. Now, to give a little bit of idea as to where we are heading, let us assume that in some locality there are 200 men and 100 women, okay, and out of which say 150 are degree holders out of men, okay, 150 men are degree holders and 60 women are degree holders. Okay. If a person is chosen at random, then the conditional probability that the person is a degree holder given that it is a man, so which we call it as the conditional probability of a degree holder, suppose if we call that as D, given that it is a man, is basically 150 divided by 200, which is going to be 0.75, and the conditional probability of degree holder given that it is woman is going to be 0.60. Right. Now, what we want? We want to encompass both this information as a single entity. Okay. The way to do this is that make these conditional probabilities as random variables by associating indicator functions as you normally do. Okay. So, what we are doing, what we are making the conditional probabilities as random variables. Now, suppose if this is what is the case, what we introduce is basically this random variable 0.75 indicator function of m plus 0.60 with indicator function of 1, where m and w denotes respectively men and woman and d denotes degree holder, right. Then this is what is, okay. So, on the set m, it takes the value 0.75, this particular quantity that we have defined. On the set m, this particular quantity takes the value 0.75, and on the set w, this particular quantity will takes the value 0.6. Now, we need to give this random variable a name. So, what we do is, we let some g to be this sigma field m and w, suppose, because your omega is 300 people and then men and women are the only two groups. So, you just say these two, this g, then you can call this random variable as probability of d given g. So, essentially what you are seeing is that probability of d given g is equal to this. So, this now probability of d given g is a random variable. If omega, that random person that you are picking, is a man, then this particular p probability of d given g will take value 0.75, and if the person picked randomly is woman, then this will take the value 0.06. So, this is what, so essentially what we wanted to do, like basically the conditional probabilities, instead of specifying individually, we want to represent that as a single entity. And how do we do that is by defining it as a random variable, and that random variable is defined through this particular sigma field g, and then this PDG gives us the required quantity, right. So, this, now let us define precisely definition. Suppose that there exists a finitely, or even you can go up to countably many sets which we call B1, B2, B3 and so on. And these sets are such that they are pairwise disjoint, and omega is equal to their union, because they are pairwise disjoint and their union is equal to omega, and G is the sigma field one obtains by taking all finite or countable unions of these BIs. G is the okay. So, this is the setting. There is a finite or countable number of sets disjoint and their union is omega, and G is the sigma field generated by these finite or countable number of sets. Then the conditional probability of A given G is defined to be probability of A given G is sum over I of probability of A intersection BI divided by probability of BI, indicator function of BI. So, what this means, go back to the previous example, you will say that on each set bi, this is nothing but the conditional probability of A given bi, and this whole quantity is what you call it as the conditional probability of A given G, and this is a random variable. Okay. If you want to write, you can also write here omega, and this is an omega. So, this is what is basically. Okay. Now, let us look at an example in this setup. Let us recall our F0, F1, F2 business and F3 in the 3 coin toss settings, where F0 is the information content of the first one toss and F2 is the information content of the first 2 toss, and the sets that we written down as the atoms for that sigma field, which is nothing but the BIs that we are talking about here, is what that partition of this omega or the atoms that generates that sigma field is what these BIs mean. Okay. Now, in that setup, we also assume that the, so you assume the 3 coin toss or 3 period binomial model setup, 3 coin tosses, okay, and assume that we toss the coin independently, and the coin is also a fair coin, means that probability of head and probability of tail both are equal to half. So, in this setup, suppose if I pick my A to be, I pick some set, so I pick this particular event as my A. Now, I want to compute probability of what is A given F1, A given F2, A given F3, and whether that makes our intuitive sense as we know about those things. Okay. So, let us first take probability of A given F1, let us try to compute what is probability of A given F1. Okay. We know F1, the atoms are AH and AT, where AH consists of 4 omegas which are starting with head, and AT consists of, so basically what we recall, A head is basically this, and AT is just the complement of this in this complete omega, which is the 8 element set that we have. Okay. Now, this is my AH and this is my A, right. So, now what is my probability of what we want to see? Probability of A given F1 is what we are trying to see. Now, as per this definition, right. So, what we need to see is that first we have to compute probability of A given BIs, and this indicator function will give you that. Okay. Now, what is probability of A intersection AH divided by probability of AH, right? We need to compute this quantity. This is what is the conditional probability of A given AH. This, since the coin toss are independent and the coin is fair, what does that mean is each of these 8 elementary events in this omega or the sample points in the sample space has an equal probability of 1 by 8 of occurring, right. So, that means A intersection AH, which will be only the element HHH, which will have an occurrence of 1 by 8, and AH, which is this, which will have an occurrence of 1 by 2, because 1 by 8 each. So, 4 of them. So, it is half, this would be equal to 1 by 4, and similarly probability of A intersection AT given probability of AT, and since A intersection AT, this is a null set. So, this is going to be 0. So, my probability of A given F1 is essentially speaking 0.25 or 1 by 4 times indicator function of A H, that is it, right. So, this is what is probability of A given F1, and similarly if I take F2 and if I want ask the question the same F2 equal to is what, then you would see, okay, let us go back and see that whether this makes intuitive sense. Okay. So, what this says is that this is essentially 0.25, this is what intuitively also you should have felt that given that the first occurrence is a head, the probability of the 3 heads occurring is essentially 1 by 4, because in the second and third task only matters, tasks are independent. So, you get 1 by 4. So, 0.25 is what then you will get here, right. Similarly, probability of A given F2 you can compute in a similar way, because my F2 now is basically I have 4 sets. So, the first one with respect to AHH, AHT, ATH and ATT are the 4 atoms, are the B's, the B1, B2, B3, B4 that we can think about with respect to this F2 is essentially these 4 sets, and A is HHH, and I can extend the same idea here to compute what is this element, and with respect to this probability of any of these sets, okay, any of these sets or sorry A given any of these sets is, if I have to compute, you would see that this is equal to half and these are all 0, right. So, my probability of A given F2 would simply be 0.50 into indicator function of AHH, and this is what naturally you expect, right. When you are given F2, the information of first 2 tasks and the probability that you are going to get 3 heads in 3 coin tosses, given the first 2 are both are heads is half and at least one tail in any of those is 0, this is what you get. So, this is what you represent as this probability of this. Now, once we have this idea, now probability of A given G idea, we can now define along similar lines as the conditional expectation of X given G. Okay. Now, recall, so first we will define, given a random variable X, we define expectation of X given G to be summation over I of expectation of X I B I divided by probability of B I as indicator function of B I, which will be the same as expectation of X given B I indication function of B I. So, this is the obvious definition, and this agrees with what we had before, because you could notice that expectation of indicator function of A given G is nothing but probability of A given G. Okay. So, this is the definition when we extend. So, what we had probability of A given B and expectation of X given A or X given B rather in the simple case. Now, when we extend, we are just extending probability of A given G and expectation of X given G in a similar fashion into this case. Okay. So, once we define this, we will now have to study about certain properties and characterizations, and that is what is going to play as a crucial role in the future when we deal with this model. So, that we will take it up in the next lecture. Goodbye.